In this lecture, I'll be discussing Lewis dot symbols for elements, which show the valence electrons. From there, the lecture will move to the process of forming molecules and depicting chemical bonds using Lewis dot structures. Along the way, I'll introduce bond dipoles. Here is a picture of a couple of hydrogen atoms. It's a very simple drawing. Each hydrogen atom has one proton and one electron. The electron is shown as a dot because we know that the electron has some particle character. We can also symbolize these hydrogen atoms by simply showing the element symbol H with a single dot to show the single electron. These are called Lewis dot symbols. The dots represent the valence electrons. If these two atoms came together to form a bond, the diatomic hydrogen molecule, then it might look something like this. We can show their overlapping orbitals with both electrons that are forming the bonds in the center. The Lewis dot structure for the diatomic hydrogen would be shown with two hydrogen atoms with a line between them. So we can use either the two dots or this line to show a pair of electrons. That pair of electrons is a covalent bond. Remember, in a covalent bond, the electrons are shared by both atoms. Remember that we can use the periodic table to determine the number of valence electrons for each type of element. So, for example, anything in group 1 has one valence electron, and any atom in group 2 has two valence electrons. We can move across just using the group numbers. And remember, sometimes I'll use an old system where this is 1A and this is 2A, and then we'll skip the transition metals and label these over here. The reason I use this is that it's written on so many of the periodic tables that are on the wall at Duke University. I just get used to using that particular numbering system. But you'll notice that, for example, over here where fluorine is, it's group 17. It's also group 7A. Fluorine has 7 valence electrons. So it works either way. What about carbon? How many valence electrons does carbon have? Thank you for submitting your answer. Carbon has 4 valence electrons. So the Lewis symbol of carbon would have 4 dots around it. We mostly use these Lewis symbols for the main group elements, and again, it reflects the number of valence electrons that are available to share. But you probably remember from the quantum mechanics discussion that carbon's 4 valence electrons are not all exactly equal, are they? So carbon has 6 total electrons. 2 of them are down here in the 1s orbital. Those are core electrons. And then the valence electrons are at the 2s and 2p sublevels. When carbon is by itself, that is a good description of where its electrons are located. However, if carbon is getting ready to make 4 equal bonds, one of the things that it does is it mixes its orbitals. It's going to mix the s and p orbitals to make 4 equal energy orbitals. We'll talk about that later. That process is called hybridization. But the point I want you to get from this slide is that carbon's 4 valence electrons are all equal. So it's fine to just show them all as dots. Here are some Lewis dot symbols of some of the main group elements. This is from a book that a friend of mine wrote, Dennis Wirtz, called Chemistry and Molecular Science. Actually, on a personal note, I read that book when my twins were about 4 months old over the course of about a month. So pretty much what I did was take care of babies and read Dennis's book. But I enjoyed it tremendously. One of the things you'll notice as you marked across the main group elements is that we're adding electrons as we go from left to right. But when we go back to a new period, so when I wrap around to the lithium period, I go back to having 1 valence electron again, don't I? Beryllium has 2. I'm skipping the transition metals. Boron has 3. Carbon has 4, etc. as we go across. Okay, so we're using these Lewis dot symbols to show the valence electrons. But the valence electrons of different elements are not all exactly the same, are they? For example, the elements are a little bit different in their electrons' energies. Here's a review problem for you to try. Let's assume I have these two fictional elements, A and B. And here I'm showing only the highest energy electron. I'm not worried about what type of orbital it's in. I'm just showing the highest energy electron. So you can see B has a higher energy electron than A. Here's a question to review a periodic trend. Which of these elements is the most electronegative, A or B? Please go ahead and answer that now. Thank you for your submission. A is the most electronegative, but electronegativity wasn't related to the energy of where the electron was it? So we're not really looking at where the electron is located for electronegativity. What we're looking at is space to accommodate a new bonding electron. So A has a spot that's at lower energy than B does, therefore A is more electronegative. The other process we learned about at approximately the same time a few weeks ago was ionization energy, and that was the process where we were removing the electron. A has a higher ionization energy than B does because this electron is closer to its nucleus and therefore it takes more energy to remove it. Here's another review problem for you to try before we move on to writing Lewis dot structures. Here I have three different elements. One of these elements is a metal, one of these elements is a nonmetal, and one of these elements is hydrogen. This is a very simple drawing showing only the energy of the highest energy electron. I'm not worried about how many other electrons there are, or even if there are other electrons at the same sublevel. I'm only interested in the energy of the highest energy electron. If you had to label these, one is a metal, one is hydrogen, and one is a nonmetal, which colored line would you label as the nonmetal? Go ahead and answer that now. Hopefully you realize that hydrogen has an intermediate energy electron between the metals and most of the nonmetals, so hydrogen would be the green one. The nonmetals here are represented by the blue electron, and this is a general trend. It doesn't always exactly work. But in general, metals have higher energy electrons than nonmetals. That's why in an ionic compound, the metal loses its electron and the nonmetal gains the electron. In Lewis dot structures, we are going to be mostly making compounds by combining the nonmetals. It is possible to draw Lewis structures for ionic compounds, but where it finds the most use is in molecular compounds that are comprised of nonmetals. So that's what I'll be spending my time on. Let's go ahead and build some interesting molecules. One interesting molecule we can build using Lewis dot structures is hydrochloric acid. Hydrochloric acid is built from hydrogen and chlorine. Hydrogen has one valence electron, and of course chlorine has 7 because it's in group 17. We can look up the electronegativities of these atoms and see that hydrogen has an electronegativity of 2.1 and chlorine has a higher electronegativity of 3.0. Therefore, the electronegativity difference between these two atoms is 0.9. That's above our threshold for a nonpolar bond, so this is a polar bond. Chlorine is not electronegative enough to completely take hydrogen's valence electrons. If that happened, then it would be an ionic compound, and the electronegativity difference isn't large enough here for an ionic compound to form. But chlorine is more electronegative than hydrogen, and so therefore chlorine gets a disproportionate share of the electron cloud. The way my friend put it is that it's enough to hog hydrogen's valence electrons. So if I drew this picture of the overlapping electron clouds and the electron on the hydrogen is red, you can see I've got the red electron spending more of its time over by the chlorine. So the cloud is not equal around both nuclei like it was in the H2 molecule. In this case, the hydrogen's proton is a little bit exposed. So the hydrogen has a partial positive charge, which we're showing with the symbol delta for partial charge. doesn't have a full positive charge. This is not an ionic compound, but it is a polar compound, and so the hydrogen is partially positive and the chlorine then is partially negative, because this particular chlorine atom has a little bit more electron cloud density around it than a normal chlorine atom that's not bonded to the hydrogen. So I'm showing a bond dipole here, right? I have a negatively charged end and a positively charged end. And another way we can show that is with this arrow that has a cross on one end. Now the way chemists use this arrow is we put the cross on the side where the atom has more positive charge. So whenever you see this little vector with a cross on the tail, that's showing the bond dipole. You can also use it to show the dipole moment of the entire molecule, and you'll see that later. So in this particular case, there's a small electronegativity difference, but it's large enough that the electron spends most of its time with the chlorine. If we were going to think about this electron that used to belong to hydrogen, and think about where it spends most of its time, it spends more of its time with the chlorine than it does with the hydrogen. So because the electronegativities are not the same, this is a polar covalent bond. And the range that's generally given for polar covalent bonds is electronegativity differences between 0.4 and 1.8. All right, so hydrochloric acid is a really simple Lewis dot structure. If I just wanted to draw the Lewis dot structure itself, I would draw hydrogen with a bond to the chlorine, and then I would draw the non-bonding electrons around the chlorine. So that's what the Lewis dot structure of this molecule would look like. Let's do a couple more of these. Now, I've used these before in lectures. You probably remembered it from the acid-base lecture, and some of you were baffled by it, even though I tried to explain what I was doing. I figured you could figure it out by the context, but now I'm actually going to go through exactly how it works. So in Lewis dot structures, there's two types of electrons shown. All of the electrons are valence electrons, but some of those valence electrons make bonds, and those are shown as lines. And some of those valence electrons are not shared between the atoms. Those unshared pairs or lone pairs are shown as dots, and sometimes you even have an unpaired dot, which is called a radical. I'm going to draw the Lewis dot structure of a couple of simple compounds. First, let's do methane. Methane is a component of natural gas. The formula is CH4. There is, for methane, a carbon, and carbon, of course, has 4 valence electrons. We've talked about that already. And then there's 4 hydrogens. Each hydrogen has 1 valence electron. It doesn't matter which side of the hydrogen I draw the valence electron on. I'm just going to draw it there on the left. When these combine, carbon is the central atom, and the pairs of electrons become lines to make the bonds. Sometimes you'll see people even draw it with the pairs as the bonds. I never draw it that way, but sometimes you'll see that. This is also a Lewis dot structure. Usually people draw the bonds as lines. So this is methane. We can count to make sure that methane has the right number of valence electrons shown. So carbon had 4 valence electrons. 4 valence electrons. Each hydrogen had 1, but there was 4 of those. So I should have 8 electrons shown. Do I have 8 electrons shown here? Let's count. Remember, every line is 2 electrons that make a bond. So I have 2, 4, 6, 8. So that adds up perfectly. Let me do one more compound. Let's do methanol. So methanol is a relative of methane. Methanol has a formula CH4O. Now, I wouldn't necessarily expect you to know the arrangement in space of the atoms. I would give you that. Let's go ahead and write that. There's a carbon, it's bonded to an oxygen, which is bonded to a hydrogen, and then the other 3 hydrogens are around carbon. All right, carbon has 4 valence electrons, and it's going to use one of those valence electrons to make each of the bonds. So it can make 1, 2, 3, 4 bonds. What about the oxygen? How many valence electrons does oxygen have? Thank you for your submission. Oxygen has 6 valence electrons. It's in group 16. So oxygen is going to use 2 of those valence electrons to make bonds, and the other 4 valence electrons remain on the oxygen as lone pairs. So this is the Lewis dot structure of methanol. Methanol, of course, has some polar bonds. Oxygen is more electronegative than both carbon and hydrogen. So I can draw some bond dipoles here, can't I? I can draw a bond dipole for this oxygen-hydrogen bond. I can draw another bond dipole for the carbon-oxygen bond. And there's smaller bond dipoles between carbon and hydrogen. If I wanted to, I could show those. Those are very, very small bond dipoles, so I'm going to just leave them off for now. So just to review, a covalent bond results when 2 atoms are sharing electrons. There's 2 situations where this can happen. One is that the bonding atoms are the same element. Usually this happens with nonmetals, but it could also happen with some late metals. You can have a metal-metal covalent bond with some of the late metals. But usually the situation is when we have nonmetals bonding to the same type of other nonmetals. Here's a bunch of examples. You can also have nonmetals that have slightly different electronegativities to make compounds. And in this case, it's still a covalent bond, but now it's considered a polar covalent bond. There's a bunch of examples given here. All of these molecules we can draw Lewis dot structures for, and you'll probably see most of those by the time we're done with this discussion. The driving force for covalent bond formation is that the system wants to lower its energy, and the electrons can go to lower energy by forming a bond. They go into what's called a molecular orbital, and I showed that back when we talked about covalent bond formation. In the process of doing this, the atoms become isoelectronic with the noble gases. Hydrogen, by forming a bond, thinks it has access to 2 electrons, and so it becomes isoelectronic with helium. The other nonmetals become isoelectronic with the noble gas that's on the right side of their period by getting what's called an octet. We'll review the octet rule in the next lecture. So this concludes the introduction to Lewis dot symbols and structures. In the next few lectures, I'll be discussing more complicated structures that have things like resonance, for example. So check those out.